Before I start, let me give you thanks, in particular the team, Rohini and his collaborators and his friends and the CHEP department here to organize this meeting. At one stage, we were thinking to have this kind of meeting, but then we came to know that already people from here they are thinking, and we came to know from Fauzi also this type of meeting is going to happen. So very nice to have this meeting, and I wish if we can organize this meeting in every year in the memory of Rohini. Anyway, so what I plan to talk here is my journey with Rohini in particle physics. In fact, I was associated with Rohini since my PhD days. Okay, so I was not her student like quote and unquote the PhD student, but I was like a student. She was also one of my mentors, and she was helpful at different stages of my life, even in my some hard times what I had. So I decided to talk about only that part which I had worked with Rohini, and so when I checked what are the few of the works, of course I know by heart, and I just checked that how many papers I have written. I checked the spares. I found that about 19 papers I co-authored with Rohini, but not all the journal papers, but some of the papers are proceedings, working groups, something like that. So out of those papers, I have selected the few topics which I think which are still relevant and will be relevant for future, in particular in experimental high energy physics for high luminosity options. First is the invisible Higgs. Invisible Higgs already Genevieve has touched upon this invisible Higgs and its importance to have some kind of claim that new physics is there through the Higgs channel, and having a branching ratio of Higgs invisible decay is non-zero. Of course, it is a standard model, it is there, but it is very, very small. It is a 0.1%, something like that. If branching ratio is more than that, then we assume that no, it is not because of the standard model, it is something else. And what is that something else? It can be the, we should think that it is a lightest neutralino, it can be the graviscalar, it can be the right-handed neutrino, it can be some kind of in the framework of extra dimension. Variety of models are there to have this where is this pointer? Pointer. Oh. So where it is? So this is the paper I think Genevieve already talked about, where they have shown that what are the various channels of to have this invisible Higgs decay, and then I think this is the first paper. I think Debojyoti and DP they talked about the invisible Higgs decay, and that time even Higgs was not discovered. So after that, they did some studies on that, and later on, we started working on that. Rohini also joined, and then that time Higgs was not discovered. We decided to look for the invisible Higgs for the intermediate Higgs range, something like 120 to 160 GeV, and we decided to consider for WH channel and ZH channel. But WH channel, the lepton it was very difficult to suppress W background, so we just didn't consider that. But then we just had this Z channel, and Z is decaying to 2 leptons, and because of this G peak, we were able to find some signal. From that preliminary studies, I think this is a study we did it at the general level, and we showed that the minimum value of Higgs, invisible Higgs, one can probe up to this value, either 77% or 42% for 120 GeV Higgs for this 30 or 121 inverse luminosity. Later on, this Higgs invisible decay, again we thought to do it at once. I was visiting here Then again we started discussing with Rohini, and then we decided to do this study BBF channel. Sitting here, I just started that work. And here I see this channel. It is found, this is the, out of the 4 Higgs production channel, BBF channel is a channel which gives the best sensitivity for the invisible Higgs. It is experimentally done it also. So we did this study at various level using more whatever that time we could do that, and these are the people who worked with us. And here when we consider the Z, we also consider the boosted Z or boosted Higgs for boosted regime. And finally we came up with these results, which are little better result than previously whatever was done. And this 17% for BBF, it is the minimum value of Higgs when invisible one can prove it. And these are the papers are very much acknowledged by both the collaboration. These papers are very much referred. Then invisible Higgs, sorry. Then what is the present status of this invisible Higgs from the measurement side data? Then you see that here CMS and Atlas, they did it. Atlas did it using the BBF channel. They are saying that 14% maximum value Higgs can have it, and CMS combined is giving the 15%. And Atlas is basically the BBF channel, but CMS is basically gluon fusion, BBF combining all these channels plus 7 TB, 8 TB data, combining everything. The important implication of this measurement is that if you think about the Higgs portal model, where Higgs acts as a portal between the known and unknown sector, then Higgs decays to some invisible, some particle, maybe the neutrino or some other dark matter particle. Then this, and the direct search also takes place. What is already Devto said, that there is collision of the dark matter with the atomic nuclear collision through the Higgs mediation. That is, if you calculate it through the EFT approach, then some way you can really connect this Higgs independent cross section and the Higgs invisible branching ratio, and then you can put the limit in this plane, where the plane is dark matter and the spin independent cross section. And here you see that this is a region excluded by the various experiment, and here these are the regions where Higgs invisible particles is predicted by some other models, and here they are excluded this. So Higgs invisible is some sort of working as a complementary approach to this search. Another important thing is the tau polarization. Tau polarization is one thing which is originally worked by these people, this Bullock, Hagiwara, and then D.P. Roy. Then D.P. Roy and Sirup, they just established the strategy how to use the tau polarization at the hadron collider experiment by looking at constructing some observable. They applied it for the charged Higgs. Okay. Then what we did is that exactly the reason of this tau polarization, why is it working? If you follow this distribution of the tau decay particle, here the tau decays this way in various hadronic channel, which is basically 65%. And these are the center of mass frame angular distribution of tau decays. And this is the x fraction of the momentum carried by the charged particle within the in the tau decay. Either it is 1 prong, or if it is a 3 prong, it is little different. Anyway, so finally it can be shown that if tau is left-handed, then left-handed means if polarization is -1, p tau is -1, then it will have one kind of this distribution of the charge track inside the tau jet, and it is the positively polarized, basically right-handed, then it will be a different. And here it is this is the distribution of the charge track if tau is right-handed polarized. So either charge track, this distribution is on the very other side, where R is defined as the fraction of the momentum carried by the charge track. So either it will be this side on the higher side or it will be on the lower side. This is the plot from the charged Higgs, okay, where Higgs is tau is coming from the charged Higgs and it is right-handed polarized. Okay, so using these properties, it is easy to suppress the background, in particular QCD. For tau, the threat comes from the QCD because QCD has lot of soft jets which really mimic the tau jet. This is a very useful quantity. So we did it. Then tau polarization is tau coannulation region. This is another important thing we did it. Where tau coannulation region means where the tau 1 and the chi10 coannulate, and that time when we did it, that time the M sugra was very popular for that kind of model. This in this case, when the tau 1 can decay to tau chi10, this tau is always, it is found to be right-handed, interestingly. And then we just studied that and did a lot of simulation. And I did it, this Pythia plus, used tau polarization handled by the tau and then CMS jet. And we shown that delta M, in this coannulation region, the mass difference between the tau 1 and the chi10, the delta, this is the Boltzmann factor sitting in the Rayleigh density calculation. It will be something like around 10-15 GeV. If it is 10-15 GeV, then this tau has to be very soft. The challenge is how to really catch the tau jet and how to really measure the mass difference at the LHC. This is another important piece of work we did it. Then Rohini said it, so you do it other way. Use this tau polarization to discriminate the models, okay, in E plus E minus. And this is, we did it, what we did it, the idea is that tau will give you either lower side or higher side, the tau jet, basically the charge part of the tau jet will give you. Then looking at the distribution, you try to see what kind of model it is. Because in supersymmetry based model, various kind of models, it is a M sugra or non-universal sugra or it is a AMSB. We have checked that the tau polarization of the tau in those decays, either 1, -1 or 0.5, plus 0.5, minus 0.5, something like that. Now you use this quantity F, amount of cross section either this side or this side, get the fraction. From that fraction you just try to identify what is the polarization of the tau, and then from there you try to get the idea about this model. So this is a very interesting piece of work. I was not very sure how much it was interesting. I did it. I just tell you one story about that. Once in the CERN theory division, the one linear collider workshop was going on, and there one afternoon, you just come up with your proposal and flash it what one can study in the linear collider. And that afternoon I just landed at CERN, and immediately Rohini saw me, oh, you are here, so you give a talk. I say, I am not prepared at this roughly after 2 hours. I just landed here. I said, I was just avoiding not to give that talk. Rohini said, no, you have to give this talk. I said, no. Finally, she made me and convinced me to give this talk. And when I was not happy, but I prepared the talk because you know Rohini comes with danda. You do it, you have to do it. And we really happy to follow that order also. And after I did it, and I just prepared the presentation. I gave the talk for 15 minutes. Somehow I managed it, and this talk was very much appreciated because this is a new way of doing the things, and they asked us to continue these things and do it more correct way to have the feasibility. But somehow we could not do this. This is another interesting piece of work, flavor volatility scale at top. Again, this is related with the some sort of related with the coannulation region. Again here, how to probe this really delta M. We did it. I think Janvieb is also part of this because of the good component of the dark matter in our paper it was there. This is the sensitivity we are showing that with the stop mass, what about the delta M we can really explore. And then this is a boosted top quark tagging, this tau decay channel. This is exactly what Tuhin said. This is the paper, I think Tuhin mentioned it. They studied the top quark is decaying into the leptonic channel. Their lepton is electron and muon. They did it, they got very nice result, and that result now is being studied also in CMS collaboration. Then Rohini asked me, Monoranjan, what about the tau? Because I have some expertise in handling tau. Then I said, yeah, in principle one can do it, then what is the benefit we will have it? Tau is also jet, okay? But finally again, no, you do it, you will have some result. Finally we did it, and I think it is Amandeep, Rohini's student, Amandeep Dey, who really we got him in this collaboration, and we did it, and we did a lot of things here. How really to tag this B and tau inside the top quark decay. It was very challenging because tau jet as a subjet, how to really eliminate it from the QCD jet. Okay, we really did a lot of work. Finally, we got some result. This is the ROC curve, and also tau, left-handed tau or right-handed tau. You know this TBW coupling, if you modify it, you can change the handedness. So this is also we tried to do it. And later on we discussed this, we did it at the card-based and the MBA level. Then Rohini said that, okay, now can we do it using machine learning more sophisticated? Basically I said that because tau jet has some properties, okay, polarization, okay. So all these low-level input can we use in the ML approach. So this is a thing we discussed it, but after that we really could not do that. Now after all these things, I just take 2 minutes to advertise my own work, which we did it very recently. Basically, how to explore the EFT operators at the LHC experiment. Here, just in a very nutshell, what we did is that I don't have to say that all this presence of EFT operator, this approach, we did it in the SM-EFT approach. We just picked up the THQ process. In this process, these are the 2 main vertex. In these 2 vertex, we identified which are the operators are important. They can play the role in affecting this process. These are the operators we have identified it. Then our next job was, these operators are not only sitting here, these operators are sitting also some top processes where top is involved, Higgs is involved. Then lot of data is there in Atlas CMS, how these operators are, in particular the Wilson coefficient are constrained. This is we really did it, calculating the cross section. Here it is standard model part, EFT part, and the interference between the standard model and EFT part would give you some deviation at the tail of the observable. So we did the calculation, keeping the 2, we just developed the technique, how to do the calculation certain way, writing some polynomial, etc. These are a lot of detail, I'm avoiding it. And this is our fitting result here. Either we took one coupling, sorry, one operator, the 2 operators, and these are the best fit we got it. Now our question is, if we trust this is the best fit value using all sorts of data, then what is the possibility we can see the effect of this operator in the THQ process at the LHC. So we did that. So this is the exactly we did that. We considered this process, and we also considered the background. We also considered the effect of EFT operators in these background processes as well. Okay. So after this, our final state, we reconstructed the Higgs, we reconstructed the top, and we had a certain number of N jets. And here you see that we divided the phase space, lower side of PTH, higher side of PTH, and lower side and boosted and non-boosted region. We can see the clear axis by which one can see the effect of EFT operator. These are the other variables. And finally, what we did is that we just divided into various slices of this phase space, and in the slices we tried to see what is the significance, signal and background, and this is our signal and background, and this is the various significance. And if you see it here, this region we can see really for this range of PTO of the Higgs, we can have really more than 5 sigma significance for 351 inverse luminosity. I think whatever we have done, whatever we said, I think today morning Sudhir very nicely, what we know, we thought to tell, Sudhir very nicely summarized Rohini's contribution in our high energy physics in India, and lot of things. I have just written few, and his administration thing and all these things. In particular, I am very much in collider physics. My collider physics interest really grew up. I learned several things from Rohini. And when we entered for the PhD, that time not many students were doing the PhD in high energy physics. Ravindran and Prakash, we were doing. At that time we thought that SSU will come, LSU will come, Treverton will be running, and LEP2 will come. We had the idea, whenever this basil will be on, lot of SUSY particles will be there. Okay, so with that kind of motivation, all of us at my age, they started working in the collider physics. So we got into that, and once we learned that, we got into that, and from our students also just along that direction. That's why I think I just addressed Fauzi's question. In India, the BSM physics, Higgs physics, a lot of people are doing, but what the actual QCD, the standard model physics, not many people are doing. But what I see now Rabindran and Prakash, they have produced a very good number of students. Those students are working here or there in our country, in various universities and institutes. They are producing students. I think that will be covered up. Yeah. So, thank you very much.